For the last several years, AI functioned primarily as a responsive encyclopedia. It sits idle, waits for a prompt, and provides a singular answer. But answering questions is a limited function. A chat interface cannot address the logistical gaps or labor shortages that stall global industries. Consider global healthcare. The World Health Organization projects a shortage of 11 million health workers by 2030, leaving 4.5 billion people without essential services. This isn't a problem that can be solved with better search results. This is why 2026 marks an evolution. AI is moving from a passive instrument into an active partner, the autonomous digital agent. These agents act on human direction to complete multi-step tasks. In a marketing context, this allows a 3-person team to execute a global campaign in days, with the agent handling data crunching and content personalization, while the humans steer the strategy. When agents manage the execution of large-scale projects, small teams can match the output of much larger organizations. This shift changes the human role from being the primary executor to acting as a supervisor for a digital colleague. Granting an autonomous agent access to internal systems and proprietary data creates new risks for an organization. You cannot integrate these digital workers into a professional workflow without first establishing a framework of control. The industry is moving toward ambient security, a system where every AI agent is assigned a unique identity and restricted to specific data access levels, mirroring the protections given to human employees. These built-in defenses monitor the data the agent generates in real time. By managing these identities, organizations ensure their agents do not become a source of unchecked risk or a target for external attackers. Establishing this level of trust is the requirement for scaling AI. Without a baseline of ambient security, an organization cannot safely offload its critical operations to an agent. Once secured, these agents can move out of the lab. In healthcare, they are beginning to manage symptom triage and treatment planning, helping to bridge the gap in clinical staffing. The shift is driven by performance. This chart shows how Microsoft's Diagnostic Orchestrator, or MAI-DXO, solved complex medical cases with 85.5% accuracy, compared to the 20% average for experienced physicians. MAI-DXO is a diagnostic AI system specifically designed to reason through multi-layered medical data. In the scientific laboratory, the agent is transitioning from a researcher that summarizes papers to a laboratory assistant that contributes to discovery. Agents are now generating their own scientific hypotheses. They are also using software to directly operate the tools that control physics and biology experiments, running tests without constant human intervention. Deploying these agents into hospitals and labs increases the frequency of experiments and the speed of treatment delivery, accelerating the pace of scientific discovery. Software development has reached an immense volume, with over 1 billion commits, or discrete code updates, pushed to GitHub annually. To manage this, developers use repository intelligence. This is a mechanism where the AI analyzes the entire history and internal relationships within a code repository, the central hub where a team stores its project files. By understanding how different pieces of a project fit together, the AI can catch errors earlier and automatically deploy fixes for routine bugs without being prompted by a developer. When the AI manages these structural details, the human developer can focus on the architectural strategy of the software, which increases the overall reliability of the global digital infrastructure. A global workforce of digital doctors and scientists requires a massive physical engine. This is forcing an evolution in the infrastructure of the cloud. Instead of simply building larger data centers, engineers are packing computing power more densely into distributed networks known as AI superfactories. These factories use dynamic routing to manage workloads. If a specific task slows down, the system instantly shifts the computing power to another job, so that no energy or hardware cycle sits idle. Focusing on this dynamic efficiency is the only way to sustainably provide the computing power needed to support autonomous agents on a global scale. Even with these superfactories, certain problems in chemistry and material science remain too complex for classical computers to simulate accurately. Hybrid computing combines 3 layers. AI finds patterns, supercomputers run simulations, and a quantum layer models molecules precisely. To ensure reliability, researchers group physical qubits into logical qubits. These units automatically detect and correct errors, enabling stable quantum calculation. This architecture is physically realized in Microsoft's Majorana 1, the first chip built with topological qubits. Topological qubits are a specific design that uses the chip's physical structure to make the quantum information more stable and reliable. This hardware breakthrough is approaching within years, not decades. For professionals, the path forward is not to compete with these systems, but to learn how to guide them. By combining human creativity with a quantum-powered workforce, we can model the molecular interactions required to develop more effective medicines and sustainable materials.